All right, good morning. Good morning. We'll dive right into this here because I've got a lot of fun stuff to cover. Basic information about me. I have been a Java developer in the past, probably since the beginning, pretty much since the beginning, but working on JRuby a lot since about 2006. Amazing that I've managed to scam multiple companies into paying me full-time to work on JRuby for the past 7 years. Hopefully we can keep that up. Now ended up at Red Hat, which seems like a nice place for us, working in the JBoss Polyglot group. And of course, as one of the JRuby developers, I'm one of the co-authors of the JRuby book. So if you're interested in JRuby, I recommend you buy many copies of it. Give them to all your friends and family if possible. So let's actually get into the content here. So who would say that Ruby is fast? It's not, it's not really the question that gets answered with yes a lot. And in fact, anybody who isn't in the Ruby community will say that Ruby is downright slow. So the question usually then ends up becoming, is Ruby fast enough? Who feels like Ruby is fast enough for what you do? Of course, most people, that answer is yes, as otherwise you wouldn't be here. If it's not fast enough for you to get your job done, you probably wouldn't be using it in the first place. So now, but fast enough is even a relative term. Fast enough for what? And what is it that we're trying to optimize for? We've got a couple different options here. We can optimize for the overall execution time of a program. That's the most straightforward, the typical way that people think about optimizing performance. Optimizing for memory use. Memory is cheap, but it's not free. If you're going to run larger instances on AWS, for example, you're going to pay to have a lot of memory and a lot of those instances running. So keeping memory use under control can be useful. Optimizing for developer time. This is a different aspect, a different metric that isn't directly related to the hardware you're running on. It's how long does it take you to get up and going, get your program running. That's an important optimization metric too. And as Michael mentioned, optimizing for developer happiness, which is a very squishy metric that's very hard to benchmark. I haven't seen any very good benchmarks for this one, but it is something that we hold very important as Ruby developers. So in order to determine what we're actually measuring or how to decide whether we've optimized enough, whether we're running fast enough, whether we're using the right amount of memory, we use benchmarks, right? Well, we can measure all this stuff, but does it actually tell us what we want to know? Does it help us improve the process? Does it help us write faster programs, programs that use less memory? Does it help us get more done in a shorter amount of time? So we have to take benchmarks with a grain of salt as we go. They are, again, relative measurements. All of these are relative to something, being more happy at what you're writing with Ruby, running code in less time. So relative to what is always important as well. Most people have seen the benchmarks game, which is a lovely set of meaningless benchmarks that everyone seems to quote all the time. Here is the overall score that different languages are given. And based on this, yeah, Ruby is not a particularly fast language. Ruby 1.9 is down there towards the bottom, a little bit better than Python 3, but not quite as good as PHP. So if we look at these in more detail, what do we actually have as far as comparison with these different languages? Ruby versus Python, looks like on some benchmarks it's a little bit faster, on some benchmarks it's a little bit slower, but Ruby and Python kind of end up being around on par as far as performance goes these days. Let's go with another enemy of the state, PHP. Yeah, not looking as good here. PHP has spent a little bit more time optimizing. It's not quite as complicated a language internally, so Ruby falls a little bit more behind. We can go with another flavor of the day, Clojure. Now we're starting to hit some more depressing metrics here as far as Ruby straight line performance, although we're doing much better on memory use. This is essentially Ruby up against the JVM. The JVM does an excellent job of optimizing straight line performance, but you pay a cost and have a little bit more memory that's being used at the same time. So Ruby does a little bit better here. Of course, there's the whole Node.js and JavaScript world, which they are among the most noisy folks saying that Ruby is not fast. Ruby is slow. You should be using Node.js. And you know, for straight line performance, they're kind of right. They do run pretty fast. They do run these particular benchmarks better than standard Ruby 1.9. But it can get even worse from there. Let's talk about Java. If you actually wanted to go all the way and write Java, Ruby is not going to be comparing very favorably as far as performance goes. And then we all get beaten at the end by C. Let's just write everything in C, because we would use less memory, we would use far less time to execute things, and maybe have a little bit more code as a result. But of course, that's not telling the whole story if we just look at these benchmarks, because the benchmarks are not actually what's important if we want to talk about optimizing Ruby, having a high-performance environment to run Ruby code in. What's important is what we learn from those benchmarks and how we can take that and improve our code, improve the implementations of the language that we love, and make better applications that run faster and do more. So now we actually get to the base of this talk, which is how we can optimize Ruby, what we can do in code that we're writing, and in the VMs that we're building for Ruby. And it all kind of boils down to the golden rule of optimization, which is simply do less work. And ideally, you do only the work that is absolutely necessary to get your application running and to get done the job you need to get done. So we're looking for unnecessary work to try and remove here. In Ruby, that ends up being things like looking up the same data that's not changing repeatedly, over and over and over again, hitting hashes constantly, constantly going after the same methods and not caching them, constantly going after constant values, global values, whatnot, static data that doesn't change. It's wasteful if we're continually doing this. On the other side, allocating too many objects. So memory actually does play into straight line performance as well. Creating objects has a cost in acquiring the memory, initializing it, setting it to something, and then later on GC, cleaning it up, returning it to the system. So these are the two big areas that we need to look at optimizing to improve the performance of Ruby code. So what is it that we want out of our programs? What do we want out of Ruby? What makes us happy as Ruby developers? Well, first of all, the fact that we can generate code at runtime is awesome. Like every new developer that comes to Ruby, the first thing they do is start evaluating code and creating methods on the fly and doing all this crazy metaprogramming stuff just because it feels so powerful, right? Injecting behavior when you need to. If you've got a module with a bunch of utility functions, you can just throw that on any object you want. Or if you've got an object and you want to change a method at runtime, add a method to it, maybe create a singleton and define some new code on it. That's another fun and fast feature and cool feature of Ruby that we like to use, right? Just creating more objects. It's free, right? Memory is free. The GC will clean it all up. Let's just create more objects as we need them. Lots of intermediate state. Makes it easier for us to follow the program. We'll just throw a lot of more objects around. And then just abstracting things more multiple levels of classes, many different broken down pieces of the same system helps us make better applications, right? Well, then we have to look at why Ruby applications actually run slow. And unfortunately, these are all exactly the same reasons. These are the problems. This is the problem with trying to optimize Ruby. There are so many of these fun, awesome features that can be useful and can be safe in certain contexts that get thrown around too much, used at runtime, totally defeats optimizations. But people continue to do this. People continue to try and use eval at runtime and wonder why programs don't run fast. They create new types. They extend modules into objects, create singleton classes and whatnot, and still don't understand why performance isn't working well, why people continue to say that Ruby is slow, why we can't compete with some of these other web frameworks and these other platforms. And it brings to mind something that Einstein said, a quote that anybody should remember. Insanity is doing the same thing over and over again and expecting different results. People don't seem to learn that there are things we can do in Ruby programs, in our applications, to improve performance, or at least make it easier for the runtimes to optimize, easier for the system to keep up with it. And that's what I kind of want to get into today. So there's two key areas that we're looking at, two areas that we can improve code in various areas of Ruby applications to improve performance, both straight line and memory use. Again, execution, calling methods and running code, looking up values, talk a little bit about how we optimize that sort of stuff. And then allocation. The data's got to live somewhere, but we want to try and keep it to a minimum. We want to try and avoid doing more allocation than is absolutely necessary for the application. So let's get into execution here. So in Ruby, we have dynamic invocation, which put simply means that we don't know what the method is we're going to call until runtime. There's some lookup that we have to do at runtime based on a target object, a method name. In some languages, we've got to look at the parameters to see which method to actually call, perhaps the number of parameters. In Ruby, it's a little bit simpler. All we need to know is the target type and a method name. But it is still an expensive process. We go and look it up on the target class. If it's not there, we need to look at the superclass. And we continue to go up the chain until we find the method that we're looking for. So we want to try and cache that. Now, if we have that method in hand, ideally, we don't want to have a whole lot of indirection. We'd like this to be as close as possible to a static call, like you would have in C or Java or something else. So the indirection can get in the way, can cause performance issues. So a lot of the runtimes, Ruby runtimes and a lot of the other language runtimes will inline methods, pull them together into the same piece of code. So we cache it, and then we can inline it, and then a lot of optimizations and a lot of improvements fall out of that. Let's look at how this actually functions in practice. So we've got our call to foo. We've got our foo class over on the other side that defines some methods. The first thing we're going to need to do is we go and look up the method. That asks the VM, I need to make this call. I've got this object in hand. I've got the name of a method I want to look up. Go and find that method for me and bring it back so we can make that call. We actually do the invocation, branch to that code, and do the call. And then ideally cache it, probably close to the main call site, the place that we did that invocation. There are other ways to cache on each class, global caches, different strategies for how we keep track of the method that we called last time so we don't have to keep looking it up in the future. Now once we have this method cached and we know that we've got the same method repeatedly and we can do things, we can go from there and do the inlining process, do some optimizations that pull methods together. So let's look at a quick pseudo example here of inlining some code. We've got a little loop that's going to call invoker. Invoker calls foo. Foo just returns a single value. Now, if we know that invoker is always calling the exact same foo method, we can inline foo into invoker. And ideally, what we get down to is that invoker essentially is just doing the same thing foo was. We've avoided the extra call and the extra cost of making that invocation. Within the loop, we can inline invoker as well. So we pull that numeric value all the way into the loop. We're not actually making either of those calls, and it's not necessary to do the overhead that goes with them. Well, now it turns out that that value isn't actually used, so we don't even make the call. We don't need to have the value around. It's not going to be used as part of the calculation. It's never seen, so we don't do that logic. And now we've got a loop that actually doesn't do anything except increment I all the way up to 10,000. And then variable I in this particular program is never read. So what we actually can get to is we can actually boil programs down to only the actual work that needs to be done. Again, the golden rule of optimization, do less work. If we can do none at all, we win. If we can do only what's necessary for the application, we win. Now, what gets in the way of this process? Well, we have this cache, and we build a lot of assumptions on this cache always being valid, always having the right target method, knowing that we're not going to have to re-look up a method, do a different branch, and figure it out at runtime. So the VM has to ensure that this cache is correct. The typical ways that we do this in Ruby is by checking that we're still calling against the same target type. So if it's always calling against string, we know that we've got the same methods for string each time. We also have to check and make sure that the method table hasn't changed. Unlike languages like C++ or Java, where the structure of the method table is largely static, determined at compile time, in Ruby the method table can change at runtime. And in fact, every class in Ruby is basically just a blank slate until you fill it with methods. So we have to be able to track that method tables are changing and methods are being redefined, methods are being added. So what does this lead us to? If we have a new type every time at a given call site, we can't cache anything. We don't know that this is the same class. We know that we're going to get a different method table the next time. The cache is defeated at this point. What if the method table is being changed every time? Well, again, we can't cache because we know that something has changed in that table and we got to go look it up again. We can perhaps make it a little more fine-grained, only look at certain portions of the table, only check if the foo method has been overridden. But in general, making modifications to the method table at runtime just makes it pretty much impossible for us to do any sort of optimization based on that method. So the problem that we have with some of those lovely features that we want in Ruby, the ones that make Ruby really fun to play with, is that we end up getting into this awful cycle. We're constantly updating the method table, we're constantly creating new types, and as a result, we have to go through this entire cycle over and over and over again. And we can't actually do any of these optimizations. And the fact that we can't cache the method means we can't do inlining, it means we can't do any of the optimizations we get out of inlining, and so our performance actually tanks as a result. There's only so much that VMs can do to optimize in this situation. So what are the usual suspects that we have causing these sorts of problems? The first one would be eval. Most people know that evaluating code at runtime is not a good idea, but a lot of people do it anyway and still wonder why the performance isn't that good. So what is it that the eval is actually doing that hurts our performance? Well, first of all, if the code is never staying the same and we're always running new code, obviously there's nowhere to cache anything. We have no constant view of the system, no static view of the methods that are being called or the code that's being executed, and so there's no way to optimize that. If the VM can't cache, it can't see any of these patterns that would inline code. It can't see values that are always static and optimize around them. It can't use constants to reduce loops, to unroll loops and whatnot. And as a result, with eval, there's really no optimization possible. You can make eval itself faster. You can do things like caching the parse tree that you used last time. But in general, you're creating new code all the time. There's no way that you can optimize it. So how do we fix this in our code? If we really need to use eval, or we think we need to use eval? Well, probably the simplest way would be evaluating that code into a static structure of some kind. Evaluate it into a method body, and then call that method. Most of the time, the code that's being evaluated at runtime is still largely static. So we can stick it into a method or into a proc or a block and call that instead. Then the VM has something it can hold on to, a method body, a call site that never changes, and we can do some of the caching and some of the optimization. In JRuby, for example, or in Rubinius, for example, if you put it into a method body, it will eventually JIT compile, it will compile down to native code, which it could never do if you're just evaluating over and over again. Now, if you actually do have some dynamic state that you want in that eval, you're doing some interpolation or other dynamic content that's being injected into it, you could just pass that in as well. Pass that into the method. Branches are a hell of a lot cheaper than evaluating code over and over and over again, even if you have a considerable number of them. Pass in a symbol for a method rather than doing the call directly. You're still going to be better off than evaluating code every single time. And ideally, if you can get rid of all evaluation in runtime in your hot path of your application, that would be best. Do the evaluation up front in your code. Get all that code created into classes, into methods, into procs, and then at runtime only hit those classes and those methods. So now Singletons, it's a little bit different. We've got that issue where we're creating new types all the time. Every time you create a singleton object out of a Ruby object, it creates a new anonymous synthetic type on that class. As far as the VM is concerned, as far as optimizing is concerned, it looks like a completely new type every time. So we have to go back, look up the methods again, do the caching again, and probably not even getting to the point where we can do the optimizations. In most cases, singletons also define new methods. So we don't even have the benefit of the method table staying largely the same. We've got both a new type and a method table that we've never seen before. There's a lot of optimizations that get defeated by that. You can even take it farther. In some implementations like Ruby 1.9 in MRI, creating singletons actually blows the method cache for the entire system because it doesn't have per class caching. It doesn't have a clear mechanism for knowing whether only one hierarchy or only one class has been modified. It has to blow away much more of the system, much more of the caches, and then all the optimizations go out the window. A special case of singletons is ObjectExtend. A lot of people have heard about DCI, basically injecting modules, injecting behavior into objects at runtime rather than having to define it up front. Apparently this is considered a good pattern by some people. But it has exactly the same effect as turning an object into a singleton. We're creating a new type so we don't cache anything. We're modifying the method tables. And even worse, we've got the whole class hierarchy is changing. Every time we do an extend of a module, we need to insert another little shim into that class hierarchy to hold a reference to it. So not only do we have one new type, we've got multiple new types in the hierarchy, and the VMs just can't even figure out how to optimize that, how to cache any of the methods that go along with it. There's actually a concrete example of this within the implementation of MRI right now. This is the implementation of IO get partial, which is used for non-blocking reads. And if you look down towards the bottom here, if we get an E would block or an E again, basically the data is not ready on the stream, it does this mod sys fail that the read would block. It's going to basically raise an exception, an error no that would indicate to the program that it's going to block, you need to loop again, try again later, something like that. Well, what does this mod sys fail do? Mod sys fail is implemented like this, and actually every single time that exception is raised, it extends a module into it. So if you're using non-blocking reads on MRI, it's doing constant singleton creation, constant extend calls, and blowing away method caches every single time. So how do we fix this sort of problem? Well, it's not actually that difficult. You can create some of these aggregate types up front. It's much better to have 100 or 1,000 or 10,000 classes that you create up front, maybe define them programmatically, but define them at the beginning of the program, rather than constantly generating new types, infinite numbers of types at runtime every time you make a call. So that's a straightforward way. There are different design patterns, different architectures that you can use. If you want to look up entity component architecture, separates the data of the application, the entities, from behavioral components, behavioral modules that then act on those entities. No need to inject behavior into your data objects that you're passing around. Just use these components, use these external representations of behavior that manipulate the data for you. And one example of fixing this, this is an issue I filed. I copied this today. It is still not resolved in MRI, even with Ruby 2.0 coming out. I filed an issue for the whole wait readable thing, wait readable, wait writable being extended into these error nodes at runtime. And it's really a trivial thing to do in almost any program. Rather than doing this extend, which feels like the cool Ruby thing to do, and the dynamic way of writing this program, just create a couple classes. So in JRuby, we actually have an E again readable and an E again writable that we just create a concrete instance of. Throw that, it looks like an E again, it looks like a wait readable, we're done. We don't have to do the extension. Very simple fix that we can make. There's actually a partial patch for MRI that hopefully we can get into one of the updates for 2.0. All right, so that's kind of on the caching side, the method invocation side. What about, for example, getting at data that we've got in memory? Most of the time, we're going to try and stick this into constants, stick it into class variables, and we'd like to optimize the access to that data as much as possible. So constants are basically just defined in tables that live on classes and modules. There's various mechanisms for looking it up, looking through the lexical scopes, looking through the class hierarchy. But in general, this data is only assigned once. Most of the time, we can cache it somewhere and save it, avoid doing that lookup every single time. What does this look like in a VM here? So we've got our constant. We ask the VM to go and look up this value. And it walks through the lexical scopes. It walks up the hierarchy, finds the value for us, and then brings it all the way back and caches it. Fairly simple. There's not much more to be done at this point since it's not a method invocation. We've got the data in hand. We cache it as close as possible to the access site to avoid all that extra overhead. But again, we have to have some way of validating that the cache is still correct. So constant lookup, as I mentioned, is both lexical and hierarchical. That makes it a little bit complicated to cache. We can't just say, look at a single target type and know that we've always got the right constant for this value, or the right value for this constant. This also means that in all the implementations I know of, cache invalidation is done against a single global serial number. Anytime a new constant is defined, that serial number flips and all the caches will have to update again. Mostly because of the lexical scope lookup. There's no way to say constant is changed in only one scope, not in another. So what sort of things actually do cache bust? Well, forcing constants to be redefined is the obvious one. If you're doing that, for example, Rails in development mode, one of the big reasons that it's slow is that, one, it has to reevaluate code. Two, it's constantly redefining all of the constants in the system. Using a lot of new lexical scopes at runtime can also be an issue. And this is not just calling a block. This is pulling in new code that has new class structures, new block structures, new method definitions. As we run into new scopes, we still have to do the caching all over again. And of course, evaluated code will do this as well. But the other surprising one is that altering class hierarchies in most implementations will also blow away the constant cache. If you're including modules at runtime, if you're doing extend, if you're doing the whole DCI pattern, on some implementations, if you're creating singletons, we're changing class hierarchies, which means that the lookup of a constant might find a different value next time. We need to blow away the caching and do it all over again. And we need to blow it away potentially over the entire system. And all constants everywhere have to be updated. So how do we fix this? Well, first of all, don't modify constants. Leave them constant. Whenever I tell folks in the Java world and in some of the other languages where they've got actual constants that Ruby's constants are not only lazily defined, they can be redefined, I always have to apologize. And I don't like having to do that. So let's treat constants as constant, and we'll get a lot better results out of them. Avoid runtime class hierarchy changes. Again, things like extend, things like singletons, the DCI pattern, they have all sorts of far-reaching effects that there's just nothing that a VM can do about that. All right, so let's move off of execution, talk a little bit about allocation. So Ruby loves objects, right? I mean, we love to just blow through objects as fast as possible. That's how we write our programs. We do lots of strings, lots of arrays. And in every single request of a Rails application, there may be hundreds or thousands of strings and arrays created. If you ever look at a memory profile of Rails running, the reason why it's not as fast as you'd like is almost certainly because of all the objects that it creates. Clojure state is also an issue. It can sometimes cause more heap data to be created just to wrap the closure and wrap the state that's around it. But it also holds objects in memory longer, causes there to be more objects there. The VM has to do more work to track all of that data. And then we've got issues as far as performance goes. So culprits here. Literals are obviously an issue. The literal string foo creates a new string object every time. A literal array creates a new array object every time, regardless of what's in it. Doing concatenation, or doing addition rather than concatenation of these different types. Most folks don't do this with array, but it's surprising how many people do string plus equals all the time and don't realize you're creating throwaway objects that are never going to be used. And slicing and enumerating. A lot of folks like to do this piping pattern where you do a map calling a select, do a map and then a select and then an inject and then some other filtering that you're doing. This is creating 3 full-on intermediate arrays for every step in that process that just then get thrown away immediately. Totally wasteful. That's where a lot of our performance ends up going. So fixing these things. Fixing literals. Again, embrace constants. If you've got mostly constant data, literal strings, throw them into constants, freeze them if you want to make sure they stay absolutely solid for you. And most of the VMs do an excellent job of optimizing this. You'll see an immediate performance improvement over just having a literal string created every time. Cache common interpolated strings and interpolated regular expressions. Most of the time for interpolated regular expressions, there's only a handful of frequently used values that people run into. And probably more than anything else, study memory profiles. I know that memory profiling tools for Ruby or for MRI are a little hit or miss. If you can run your whole application or subsets of your application in JRuby, you'll be able to get some of those memory profiles. And even if you don't use JRuby eventually, you'll be able to hunt down some of those issues and fix it for your MRI-based apps. Fixing concatenation and copy. Obviously, modifying in place is nice. That does lead to some thread safety trade-offs. Hopefully, a few folks were able to see the immutable Ruby talk yesterday. A nice way to avoid the issues of creating too many objects, too many intermediate lists, and doing a lot of copying, and still be thread safe is to use persistent data structures. Take a look at the library called Hamster, which has the ability to do these persistent structures, immutable structures that you still can sort of mutate or feel like you're mutating. And then fixing enumeration chaining. Well, condense it into fewer steps. That's probably the best result. Don't do the chain in the first place. Lazy enumerator in 2.0 will kind of pipeline the values through rather than creating a lot of the intermediate results. It's one of the reasons it was added. Hopefully, folks will be able to start moving to 2.0 in the near future. I think there is a pure Ruby implementation of this that you can use as well. Depending on the sizes of your lists, even having a pure Ruby implementation may be a win. Or just use a loop. You don't have to necessarily use all these closures and pipeline it through with these intermediate lists. Just loop over the values, make the changes, do the next loop. You're going to have a better result for performance reasons. So now, what do you get out of this if you make some of these changes in your application? The case study here is the one I know best, which is JRuby and the JVM. So we run on the JVM. We get the JVM optimizations for free. Over time, the JVM gets faster. As a result, JRuby gets faster. But JRuby itself, we're also improving over time, applying a lot of these same strategies to the JRuby code base. And everything that I've shown you here, we're doing some form of that to optimize JRuby internally, and then in turn using that to optimize Ruby code. So what if we actually stopped working on JRuby and just let the JVM guys do their optimization? Well, this is a graph of JRuby 1.0, 103, from Java 1.4, which was the version available back in when we were working on it, all the way up through Java 7. And if we had done no work at all, JRuby's performance would have improved 300%. Just because the JVM guys are applying these same sort of strategies, trying to avoid the cost of doing method lookups, trying to reduce the amount of memory allocation or improve where you're doing memory allocation. And actually, if we had just sat there and done nothing since 2006, we would have actually passed Ruby 1.8 as far as performance goes, just by letting the JVM guys do this. So how do we get this out of the JVM? Well, we turn Ruby source into our AST. We eventually compile that into JVM bytecode. The JVM bytecode will take that, run it through its interpreter, and eventually turn it into native code. And then this process can kind of cycle. It'll actually improve the native code over time. So by being able to have a static view of the system, methods that don't change, caches that stay valid, we can eventually get all the way down to native code and get considerably better performance than on MRI. So now let's actually look at JRuby improving over time. This is on OpenJDK 8, which is in some preview releases now, all the way from JRuby 1.0 up to JRuby 1.7. And here we have an 800% improvement, eight times better over the process, over the years of working on JRuby. And you'll notice that at the beginning here, there's a major jump from JRuby 1.0 to JRuby 1.1. Well, this actually falls into the allocation bin. In JRuby 1.0, ObjectSpace was an available feature all the time. But there's a caveat there. On MRI, since objects never move in memory, it doesn't have a copying collector, it doesn't have a compacting collector, walking all of the objects in memory is simply just walk through the entire heap, walk through the entire memory space, and list all the objects. On the JVM, objects move all the time. That's how it gets good performance out of garbage collection. Old objects get moved to a separate memory space that it doesn't scan as often. So walking all objects in memory is much more difficult and much more expensive. And in JRuby, we actually had to track all those objects separately in our own data structure. So creating a second wrapper in a list somewhere just to be able to implement ObjectSpace. If we run JRuby 1.0 with a red-black benchmark here, we have dozens and dozens of GC runs happening for every iteration of this benchmark. That's where all of our performance is going, and it's all due to the allocation of extra objects, unnecessary objects, that just blows away performance. Look on JRuby 1.0, there's maybe one garbage collection cycle for each one of the iterations. So let's take out that first outlying performance bump there. And towards the end here, you actually see that we get another big improvement. Well, this is, again, us taking better advantage of the JVM, better advantage of how it optimizes using InvokeDynamic. So performance-wise, as far as JRuby on the JVM, we compiled onto JVM bytecode. It compiles into native code, and it has an amazing JIT that can then turn that into the optimized code for the processor. InvokeDynamic makes this even better for us because it allows us to teach the JVM exactly how Ruby works. Dynamic calls can inline like we want them to. All that extra work that's being done can be boiled away. Constants can become truly constant if we access them multiple times. If we make branch decisions based on them, we can fold those branches away and see that ahead of time. And actually, the JVM is now starting to get to the point where when it inlines this code and optimizes it, it can even get rid of some of those allocations. So transient objects that aren't necessary start to go away. If we look at an example of this actually happening with JRuby on InvokeDynamic, here we have our block, our little loop that's running the invoker calls. This is the next level down, and the JVM is actually inlining the I less than, the fixed num less than logic here. We've got the invoker method being inlined as well. The foo method is being inlined. And this is all being pulled into the same piece of code. And then even down at the bottom, the increment of that fixed num every single time all gets inlined into one piece of code, and the JVM is able to see how to do this optimization. And this is if we've got the static view, we've got mostly unchanging method tables, and we've got constant types that we see when we run. So the payoff for all this, how does actually improve performance for JRuby? How does it help us run better over MRI? How will it help your code run better just by making some of the same strategies? So the numbers I have are the numbers I know for JRuby. Talk about JRuby on Java 7 with and without InvokeDynamic versus Ruby 2.0 on a couple different benchmarks. Base 64 is just doing a base 64 encoding. Richards is kind of like a kernel event pipeline simulator. Neural network is like a neural network 101 implementation, and Mandelbrot is just a fractal. So here is JRuby, how many times faster than MRI it is on these different benchmarks. And then InvokeDynamic, again, by being able to give the VM a more static view of the system, it's able to take that and run with it and do a lot better optimizations. Another benchmark here, smooth sort, recently re-implemented in Ruby by Chuck Remus. So we take a look at this on a couple different implementations. We've got Ruby 1.8.7, which definitely was not fast. I think we can safely say that now. 4750 iterations of a medium-sized sort, or a small array sorted every time. Ruby 1.9.3 does improve on that. It was about twice as fast as Ruby 1.8.7 for most benchmarks that I've run. Ruby 2.0 actually does a pretty good job on this as well. They've reduced some of the allocation that they do normally by reducing frame costs, reducing the amount of overhead for every call, applying the same strategies here just to optimize Ruby internally. And then, of course, JRuby, we do considerably better on this one. But it's only because we've got both our work on the JRuby and the work on the JVM, all of which are just trying to make the system more static, make things more cacheable, reduce the amount of objects being allocated. And then the big one here, the rbtree extension. There's a pure Ruby version that works everywhere for simple red-black tree. And most people that are using the red-black tree stuff will actually go to the C extension or a newer Java extension to get full-on performance out of it, to get the speed that they need. But maybe we can actually compete with that. So let's look at this. We've got different combinations of the pure Ruby version and the native extension versions across a bunch of implementations. Ruby 1.9.3 with the pure Ruby version takes 3.96 seconds for every iteration of this benchmark. Ruby 2.0, again, nearly twice as fast. So I don't want to malign the work that's being done on MRI at all. They are making substantial improvements with every major release. Maglev is the gemstone Smalltalk-based Ruby, about twice as fast as Ruby 2.0 on the pure Ruby version. MacRuby is slightly better. It does a good job of optimizing certain things, other things not so much, but it beats out Maglev a little bit here. Rubinius drops it down quite a bit. And Rubinius, again, because it has inlining optimizations, because it has constant optimizations, because it actually can get stuff down to native code, Rubinius with Ruby actually performs pretty much like Ruby 1.9 with the C extension. So Rubinius guys are applying a lot of the same strategies here to optimize code. Ruby 2.0 didn't quite improve as much with the C extension here because the work that was done on optimizing Ruby 2.0 was all in the Ruby space. The C extension is still largely the same performance, and that's where the bulk of the work is being done. Now, the fun part here is JRuby running the pure Ruby version. Almost twice as fast as Ruby 2.0 or Ruby 2.0 with the C extension, or Rubinius with the Ruby version. And then, of course, with the Java extension, it boils down to much less. We're actually doing considerably better because the VM has able to optimize not just the Ruby code, but the Java code the exact same way. So what's the lesson that we learned from this, other than that JRuby's awesome? So the first lesson is that performance doesn't just happen. You're not going to be able to just sit there and hope your applications are going to get faster. Even if you have folks like the JVM guys working on it, the 300% improvement is not enough over the course of 6 or 7 years. And telling your client, we just need to wait 6 or 7 years, probably is not going to get the answer that you want. So you really need to understand how Ruby gets optimized, what happens under the covers to make Ruby run fast in these different VMs, what the strategies are. Study memory profiles so you know where all this excess allocation is happening and so that you can reduce it. And really, don't expect the impossible from the VM guys like me. There's only so much we can do, and by understanding how Ruby code optimizes and the cost of allocating these objects, you're going to get better results. And ultimately, don't let the FUD about Ruby being slow get you down. There's a lot of great work going on, and there's a lot that you can do in your own programs to make it easier for Ruby to be fast. All right, thank you.